My name is Dan Shumsky. I'm an independent scholar. I live in Davis, California. I am the author of the least action nuclear process model of cold fusion that we'll be discussing today. Low-energy nuclear reactions, or what has more commonly been called cold fusion, is finally a reality. Researchers worldwide are learning how to produce heat energy in very simple, low-temperature nuclear reactors. And what makes this type of energy production so remarkable is the absence of radiation emissions or radioactive end products of any kind, just abundant and inexpensive clean energy. But despite 25 years of scientific research and thousands of successful experiments, all that we can say about the cold fusion process is that it is nuclear and it can produce a lot of heat energy. But no one can tell you how it works. It is as if the underlying process defies the laws of physics, acting more like a perpetual motion machine than a nuclear reactor. But unlike perpetual motion, which produces as much energy as it consumes, these experiments produce a lot more energy than you put into them. There is little doubt among cold fusion researchers that the excess heat production is real and that the underlying process is indeed nuclear. But you've got to ask, how does it work? This is the story of the least action nuclear process, or the LANP theory of cold fusion. It's a new theory that takes a bold step. It treats the cold fusion process as if it were thermodynamically reversible. Now, physicists cringe at the suggestion of a thermodynamically reversible process. Such a process is thought to be only an ideal case, something that doesn't actually exist in nature. But if it did exist, it would lie at the very limits of the second law of thermodynamics, where time essentially stands still and energy transformations take place in very unexpected ways. You are about to enter a twilight zone, where we will walk in the domain of reversible thermodynamic processes and even perpetual motion. Our story begins in 1989 when Martin Fleischmann and Stanley Pons announced to the world that they had succeeded in experiments that produced more energy than they consumed. However, these researchers went further, saying that the amount of heat produced could only have its origin in a nuclear process. Their experiments of palladium electrolysis in heavy water would eventually give way to experiments using inexpensive nickel electrodes, making commercialization of this phenomenon a real possibility. We're going to be looking at these nickel electrode experiments. The electrolysis takes place in heavy water, water where the hydrogen has been replaced with heavy hydrogen or deuterium atoms, and where the hydrogen contains, in addition to the usual proton, a neutron. Heavy water can be acidified to produce large numbers of free deuterium nuclei called deuterons. We'll be looking at a cold fusion electrolysis experiment where the cathode is a nickel wire. It's not pure nickel, but rather nickel with other metal impurities such as silver, cadmium, copper, and platinum. In addition, there are usually non-metal impurities. Silica, calcium, and magnesium are common. And the experiment passes an electric current through the nickel wire, thereby introducing free electrons into the apparatus. When we get up close and personal to the nickel electrode surface, we find that there are four kinds of energy present. The electrical energy of the electrical current, the chemical free energy between the heavy water and its acid-base constituents, the internal blackbody heat radiation spectra at the device's temperature, and the energy of molecular motion of the individual molecules and ions. The last of these, the heat of molecular motion, will be central to our inquiry. Nickel absorbs hydrogen ions, or in our case, deuterons, to form nickel hydride. It's essentially nickel with a lot of hydrogen dissolved in its metal lattice. We're not going to concern ourselves with the mechanisms of nickel hydride formation, but instead focus on the flow of energy during the deuterium absorption process. In particular, we'll contrast the energy of molecular motion in the nickel electrode, where there is virtually no kinetic energy present, to the tiny deuteron, which exhibits a lot of motion, and thus a lot of kinetic energy. A single deuteron's kinetic energy is 1/2 of the product mass times velocity squared, or 1/2 mv squared. Now, at the moment of deuterium absorption, the kinetic energy of the deuteron becomes identically zero. But the kinetic energy is not lost. The first law of thermodynamics requires that it be conserved. We will assume that it is retained in the lattice structure of the nickel electrode, and in this way, heat of molecular motion is harvested and stored in the nickel hydride lattice. If we make some reasonable assumptions about the amount of kinetic energy in the deuterons, we find that it would take only a few atomic layers of the deuterium-saturated nickel wire to store enough energy to facilitate cold fusion ignition. The next question that we have to ask is, how is the energy stored? What mechanism allows energy to accumulate to the point where it can sponsor nuclear reactions, and do so in a way that we cannot detect the ignition energy's presence in our experimental device? To answer that question, we have to look back to 1958, when Rudolf Mossbauer conducted a very clever experiment using a spring-loaded mechanical device, a toy's mechanism, to show that metal nuclei could absorb and emit high-energy radiation without any loss of energy to recoil. His discovery is now called Mossbauer resonance, and it won him the Nobel Prize the very next year. The thing that made Mossbauer's discovery so important was his observation of a high-energy, reversible thermodynamic process in nature. These are processes where no energy loss occurs, and the process exhibits the fundamental characteristics of perpetual motion. Well, you might ask, how can this happen? Let's consider a photon. We will look at it as a one-dimensional quantity, h nu, which travels through space without any change of state. It is truly a reversible thermodynamic process until the first moment when it encounters a material particle. Let's take a closer look at that absorption. Consider the possibility that absorption is a two-step process. In the first step, the one-dimensional photon is completely absorbed by the electron and remains in its one-dimensional state. Then, in a second step, the photon transforms into the three-dimensional coordinates of the electron. In essence, it divides into its two components. The electrical vector transforms to 3 dimensions, resulting in a contribution to the electron's three-dimensional charge. But there is no equivalent three-dimensional form for the magnetic vector's evolution, and it remains as a one-dimensional paramagnetic spin. The photon has now undergone a transformation from its reversible thermodynamic state to an irreversible state where electric charge is continually going over into the heat of motion in a process called dielectric loss. This dielectric loss alone characterizes the irreversible thermodynamic state of an electric process. In essence, photon decoupling has distorted the space-time fabric and given rise to the black-body spectral form that Max Planck discovered in 1900. It was a theory that introduced the quantum into physics. We might say that the photon itself has transformed from its reversible state to an irreversible state. Now consider the possibility that the fully absorbed one-dimensional photon, instead of transforming to three-dimensional, can instead be emitted as a one-dimensional photon of exactly the same energy as the absorbed photon. This is precisely what Mossbauer found. In his experiments, a gamma photon is fully absorbed in its one-dimensional state only to be immediately re-emitted, again in its one-dimensional state and at exactly the original energy. This is called resonant fluorescence. It is common in nature. Now let's take a step beyond Mossbauer's discovery and conduct a thought experiment where the emitted one-dimensional gamma photon is then absorbed by an identical nuclei, again with no energy loss, and then emitted again without energy loss, and so on. In fact, let's place the absorbing and emitting nuclei in very close proximity to each other, so that the absorption and emittance occurs continually between them. This is now a time-independent, reversible thermodynamic process. Well, let's give it a name. Why not call it a metallic bond? After all, it is energy locked between two metal atoms. It keeps them close together and without loss of energy. In theory, this bond should be able to continue indefinitely, which is exactly what we see in nature's metallic bonds. In fact, why not go one step further and call this perpetual motion machine a metallic bond where the energy is shared between identical nuclei and a covalent bond where it occurs between electrons. This covalent bond is essentially the model found in quantum electrodynamic theory. It explains, for instance, why the covalent bonds in a piece of wood found in an ancient Egyptian tomb retains its form and its heat content over thousands of years and indefinitely into the future. This covalent bond energy is evident when the wood is burned or when it is used as an energy source by decomposing organisms. Now we're ready to explore how this two-step photon absorption might change the way that we view heat processes. When we add heat energy to a material that is initially at equilibrium, two things happen to the black body spectral curve. First, the Wien frequency, that where the spectral curve is at its maximum, advances to its next value. And second, another layer is added to the spectral curve, that is, a single quanta of energy is added at each frequency. The temperature has just increased 1 unit. In our cold fusion electrode, each quanta of energy added to the spectral curve is a new covalent bond between electrons or a new Mossbauer resonance between nuclei. The single concept that makes LANP theory so attractive is the way that it deals with heat energy storage in non-equilibrium and far from equilibrium states. We can probably agree that cold fusion is a very far from equilibrium heat process. This is a place where physics has no theory, and most certainly not one that can address far from equilibrium conditions. And yet, here we are asking questions to which such a theory is central. The LANP theory addresses this need directly by introducing a new equation into physics. Its black-body equation differs from Planck's in the way that it has two temperatures. One described as the mass domain temperature, T sub m, which is the familiar thermodynamic temperature used elsewhere in physics. It is in essence the temperature due to thermal motion. The other is what we will call the radiation temperature, T sub r, that describing the temperature contained in a system's chemical bonds. Remember the photons being absorbed and re-emitted between covalent electrons or Mossbauer resonant nuclei? At equilibrium, Tm and Tr are equivalent, and their temperature describes the equilibrium black-body spectral distribution announced by Planck in 1900. But the beauty of the black-body spectral equation arising from this theory lies in how it behaves when we separate the two temperatures in a very far from equilibrium way. We're now ready to do some clever calculations. We'll begin with an equilibrium black-body spectral curve. Let's hold the radiation temperature constant and increase the thermodynamic temperature. This might be the initial condition if we introduce heat into an object by friction. It causes the far from equilibrium black-body spectra to rise while the Wien frequency remains constant. This is heating by molecular motion alone, and at the moment that it is introduced, all of the introduced energy is heat of molecular motion. Similarly, we can cause the exact same amount of heat to be imparted to an identical object by exposing it to radiation, the sun, for example. Now the spectral curve moves to the right. The Wien frequency increases, and take special note of this, it does so without any increase in the system's thermodynamic temperature. We are storing ever-increasing amounts of radiation domain energy, but all the while keeping the temperature of the physical system at room temperature. Both of these cases evolve to identically the same equilibrium temperature, and at that point, there's no way to distinguish by which method the object was originally heated. Also notice how heat moves continually between the mass and radiation domains and always in the direction of equilibrium. In fact, it is difficult to move heat storage in the opposite direction, away from equilibrium, and almost impossible to keep it there. But as we are about to see, it is not impossible. Consider what happens when kinetic energy from the deuteron is absorbed into the metal lattice, where it then resides as resonant energy between electrons or nuclei. Once that bond is formed, there's no way back to the previous energy state. The kinetic energy is transformed to a photon that resides between these subatomic particles and is in fact locked there in a very stable way as a chemical bond. What we have just described is a branch to what would otherwise be an inaccessible thermodynamic state. Nicholas and Prigogine have called the ordered state that emerges in this manner a dissipative structure. Now notice what is happening. As the far from equilibrium black-body spectra is filled, the radiation temperature is increasing incrementally on its way to what will ultimately be solar temperatures in the cold fusion device's nickel electrode. Now that is a bizarre concept, solar temperatures in a room temperature device. But that is what is required. Our process is thermodynamic and hence temperature specific. Energy storage by itself is not a sufficient condition for nuclear ignition. The cold fusion process needs solar temperatures. If we are going to understand how this is possible, we need to take a little closer look at temperature, and more specifically at what exactly the radiation temperature is measuring. Temperature is a derivative. By convention, it is measured as the radiant heat coming off an object, or more precisely, the spectral emittance in the interior of the object. At thermal equilibrium, the emittance is distributed as a familiar black-body spectra that is dependent only upon the temperature. It is independent of the object's material composition, and as it turns out, it is also independent of its size. When we measure temperature, we will be equally successful measuring either the thermodynamic temperature with, for instance, a thermometer, or the radiation temperature with, for example, a bolometer. And as long as the thermal system is in equilibrium, either of these is a sufficient measurement. However, the non-equilibrium or far from equilibrium temperature conditions that we are going to be considering in the cold fusion context are very different. Energy that enters the radiation domain, our chemical bonds, has no recourse to the mass domain. The two temperatures act independently, a constant mass temperature, Tm, and as we will see, an always increasing radiation domain temperature, T sub r. So let's measure the temperature of the covalent bonds that store the radiation domain energy. The emittance from either of our resonant electrons or nuclei is identical and equal to the quantum energy, h nu, multiplied by the number of times it occurs each second, i.e., the frequency of the photon. Thus, the temperature is proportional to h nu squared. At low quantum frequencies, the temperature of covalent electrons is low. However, as the frequency increases, the temperature increases as the square of the frequency and approaches solar temperatures as gamma frequencies begin to appear. Thus, two atoms in Mossbauer resonance are extremely hot and essentially at solar core temperatures. But they are in a device having the modest thermodynamic temperature of the laboratory. This is precisely what is required for nuclear fusion and fission reactions, and precisely what is happening in a cold fusion reactor. Ignition occurs when the radiation temperature within the electrode approaches solar core temperatures. Our observations that nuclear reactions occur in cold fusion devices tells us that it is a sufficient condition that the radiation temperature alone approaches the ignition criteria. So now we have a device that at what is essentially laboratory temperature to an observer, but which masks its true temperature, that existing between subatomic particles in the metal lattice nuclei. I want to be sure that you understand how both the energy storage and the true LANP temperature are masked from our observation. There is one extremely important issue where the LANP model is silent. How does it mechanistically overcome the Coulomb barrier? We know that there is an answer to this question because nuclear fusion reactions clearly occur. We just don't know what the answer is, at least not yet. This doesn't mean that we should abandon the LANP theory. Rather, we should look at this as an opportunity for an incredible scientific discovery. Before we go on, let me take a moment to look at the issue through the lens of the LANP theory in its current state. And in particular, let's look at the possibility that quantum electrodynamics may be poised to solve this important shortcoming. Consider the possibility that the gamma energy storage within a Mossbauer bond might be causally related to the distance between the two nuclei. Is it possible that the radiation domain energy storage on its own might be sufficient to overcome the Coulomb barrier? Let's continue. So what kind of reactions occur in the cold fusion apparatus? As it turns out, any reaction that can occur at the operative radiation temperature is a candidate. However, because we are dealing with a reversible thermodynamic process, the reaction that actually occurs next from all of those that are candidates is the one that satisfies the principle of least action. And in our case, that translates to a reaction that results in the smallest mass change in the product nuclei. Dr. George Miley at the University of Illinois has conducted a remarkable group of cold fusion experiments where he measured the isotope composition of his initial electrode and then his final electrode. He intended to verify the nuclear transmutation measurements of Tadahiko Mizuno. These measurements show that there is a large number of new isotopes that were not present at the beginning of the experiment. Even more remarkably is their observation that the final isotope composition differs significantly from naturally occurring isotope percentages. And it does that for each of the elements in the electrode. Let's look at a nuclear reaction that might occur in George Miley's experiment. Nickel-58 fuses with silver-107 and a single deuteron. Classical physics tells us that osmium-167 should be the initial product of the nuclear fusion reaction, and because it is unstable, it decays down a complex decay sequence to 39 radioactive intermediate isotopes and 7 stable isotope products. Of these 7, only 3 were observed in Miley's final electrode. How did the cold fusion process select for these 3 stable isotopes? Or did it? The answer lies in the principle of least action, which unambiguously determines the next step for any reversible thermodynamic process. In the present case, if we calculate the total mass change between the initial reactants and each of the 7 stable isotope products, we find that erbium-167 results in the smallest mass change, plus 0.0776 atomic mass units. Erbium-167 is believed to alpha decay to dysprosium-163, resulting in an even smaller total mass change of plus 0.0768 atomic mass units. The principle of least action has selected from among the 7 stable isotope products the one that is produced in this nuclear reaction in Miley's electrode. But there is more. The alpha particle produced in the transformation of erbium-167 to dysprosium-163 appears in the experiment as helium gas. So, the helium measured in so many cold fusion experiments may not have its origin in deuterium fusion, but rather as a byproduct of alpha decay to least action products. Have you noticed that we always include the algebraic sign of the least action mass change? Some are negative, indicating a nuclear reaction that consumes heat energy in accordance with Einstein's equation E equals mc squared. Others have a positive mass change, indicating the release of heat. But experimentalists do not measure the individual heat uptake and releases. Rather, they produce a time history of the net heat effect. So, if there is a predominance of heat-producing nuclear reactions, the experimentalist sees heat production, and the experiment is declared a success. But what happens if the endothermic or heat-consuming reactions predominate? The experimentalist is looking for excess heat and may not have the ability nor the inclination to look for heat consumption. The experiment is declared a failure. But that is not necessarily true. The LAMP theory predicts that nuclear events have occurred and at room temperature, but they have simply gone unnoticed. Finally, it's important to note that both fusion and fission reactions appear to occur in the LAMP reactor. All of these nuclear reactions, regardless of whether heat is produced or not, emit or consume relatively large amounts of energy. This is always in the gamma energy range, and therefore it should be easily measured while the LAMP process is operating. However, this is not necessarily the case. With rare exceptions, no form of radioactivity is ever observed. So what happens to the energy given off by these nuclear fusion and fission reactions? Remember, we are dealing here with a heat process, one that differs from any other that science has ever encountered. Not only does it produce nuclei that were not present before the outset of the LAMP heat production, and generate heat in quantities that can only be explained as nuclear, but it does so without emitting any of the radioactive byproducts that are expected. Now, the first law of thermodynamics requires that we either, 1, see these gamma photons, or 2, account for them in some other way. So let's take a look at gamma emittance through lens number 2. When we do, the result is very satisfying. We find that the process is doing precisely what it's supposed to do, conserving energy. In particular, we find total energy production that is consistent with gamma energy producing nuclear reactions, but it is simply in the wrong form. It exists as low energy heat rather than high energy gamma radiation. This is consistent with the first law, which only requires that the amount of energy emitted during LAMP is consistent with the amount given off by the operative nuclear process. It is not necessary that the observed energy, in our case low intensity heat photons, be in the expected form, high intensity gamma photons. It is a sufficient condition that the energy conservation principle is satisfied. So, there has to be a process that takes the high-intensity gamma photon and transforms its heat content into low-intensity infrared photons. The LAMP theory explains this paradox in a straightforward manner. Consider the microwave that you used this morning to reheat your coffee. It emits microwave radiation in the 2.5 gigahertz range and imparts that energy to your coffee. But the radiation coming from your coffee is a frequency-transformed representation of the original microwave energy into a lower energy representation, but having essentially the same total energy. A similar frequency transform occurs in the LAMP reactor. The gamma photon is absorbed into the far from equilibrium blackbody spectra, where it is transformed to lower energy photons that are spread over a large number of low frequency energy quanta. The summation of them is the total energy of the original gamma photon. It is also noteworthy that no other radiation or radioactive waste products result from LANP operation, nor do we see half-life decays. The nuclear transmutations seem to occur directly between the stable isotope reactants and the final stable isotope products. There is no trace of unstable intermediate isotopes or their decay products. For example, the LAMP model speculates that the fusion reaction of nickel-61 and silver-107 with two deuterium nuclei might occur. This diagram from my original calculation set shows the normal decay sequence for the iridium-172 fusion product. The normal decay occurs along four pathways, two of which converge. There are two stable products that are not in Miley's final electrode, and one that is, ytterbium-172. The least action change calculation selects for ytterbium-172, but it is particularly noteworthy that the normal half-life decay of hafnium-172 to lutetium-172 is 1.87 years, far longer than the experiment duration. This illustrates a particularly noteworthy characteristic of these reactions when they are treated as reversible thermodynamic events. Only the initial and final states are operative. The mass-energy conversions occur completely independent of the normal intermediate states. In other words, half-life time delays and the intermediate radioactive products never exist within the LAMP device. This is a new type of nuclear decay unknown to modern science. I call it sigma decay. So let's summarize the LANP process. 1. LANP is a nuclear process, but it produces only stable isotope products and no radioactivity or unstable isotopes. 2. It is a reversible thermodynamic process. 3. Its theory requires two elements of new science. First, a theory of heat, wherein heat energy is stored in both the radiation domain and the domain of molecular motion. Secondly, a modification to the quantum electrodynamic description of photon-electron interaction that includes both reversible and irreversible photon absorption. 4. LAMP acquires its ignition energy by harvesting the waste heat of deuteron motion in a thermodynamically reversible manner and storing it as radiation domain energy between subatomic particles. This energy storage mechanism masks that energy from our observation. 5. LAMP produces solar core temperatures between nuclei where it remains undetectable. 6. The LAMP process produces both fusion and fission transmutation and emits helium-4 as a result of alpha decay. 7. Both heat-producing and heat-consuming nuclear reactions occur, and it is the predominance of one over the other that determines excess heat or no heat production. However, in both cases, nuclear transmutations occur within the metal lattice. 8. The LAMP selects for stable transmutation end products according to the principle of least action, and in particular for the reactions that produce the smallest overall mass change. 9. LAMP produces no radioactive nuclei or radiation emissions, and exhibits none of the half-life decays of normal nuclear decay. Only the initial and final states are operative. This decay process is called sigma decay. 10. Its gamma radiation products are absorbed into the far from equilibrium blackbody emittance spectrum, where they are frequency transformed into multiple low-energy heat quanta. And finally, LAMP will change the world in fundamental ways. It is my personal opinion that we are standing in the lull before a scientific revolution that has the potential to leave all of us in a state of awe.